Classification of computing based on the capability and utility. Traditional or classical computing refers to the use of binary systems, zeros and ones, to perform calculations and process data using classical bits. It follows deterministic algorithms and is the foundation of modern digital computers. An example is a personal computer, PC, which uses a CPU to execute instructions in software programs, like running a web browser or word processor. Analog computing uses continuous physical phenomena, such as electrical voltage, to model and solve problems. Unlike digital computing, which processes discrete binary data, analog computing handles data in a continuous range. An example is a slide rule, which uses logarithmic scales for multiplication and division, or an analog computer in early aviation, which calculated flight paths based on continuous input signals. Supercomputing involves using extremely powerful computers, called supercomputers, to perform complex calculations at high speeds. These machines handle vast amounts of data and execute trillions of operations per second. An example is Summit, a supercomputer developed by IBM for Oak Ridge National Laboratory, used for research in areas like climate modeling, genomic analysis, and simulations of nuclear reactions. Cloud computing delivers computing services, servers, storage, databases, networking, software over the Internet, the cloud. It enables scalable resources and on-demand access without direct management by users. An example is Amazon Web Services, AWS, which offers various services like EC2 for virtual servers and S3 for storage, allowing businesses to run applications and store data remotely, reducing the need for on-premises infrastructure. Edge computing brings computation and data storage closer to the location where it's needed, reducing latency and bandwidth usage. It processes data locally, near the source, rather than sending it to a centralized data center. An example is autonomous vehicles equipped with edge computing devices to process sensor data in real time, enabling quick decision-making without relying solely on distant servers, enhancing safety and efficiency on the road. Fog computing extends cloud computing to the edge of the network, enabling data processing and storage closer to the data source. It bridges the gap between IoT devices and cloud services, offering low-latency data processing and reducing network congestion. An example is a smart city infrastructure where fog nodes deployed throughout the city handle data from sensors and devices, enabling real-time analysis for efficient traffic management and public services. Quantum computing leverages quantum mechanical phenomena like superposition and entanglement to perform computations exponentially faster than classical computers. Unlike classical bits, quantum bits or qubits can exist in multiple states simultaneously, enabling parallel processing. An example is Google's quantum processor Sycamore, which demonstrated quantum supremacy by solving a problem in 200 seconds that would take the world's fastest supercomputer thousands of years to solve, showcasing quantum computing's potential. Biological computing explores the use of biological molecules, such as DNA, proteins, and cells, to perform computational tasks. DNA computing, for instance, encodes information in DNA sequences and utilizes biochemical reactions for computations. An example is DNA-based computing for solving complex mathematical problems, optimizing molecular designs, or even storing vast amounts of data with high density and durability, showcasing the potential of biological systems in computing. Optical and photonic computing employs light instead of electricity to perform computations, promising faster processing speeds and lower energy consumption. Photonic devices manipulate photons, utilizing their properties like wavelength and polarization for data processing and transmission. An example is photonic integrated circuits, PICs, which integrate various optical components on a single chip, enabling high-speed data communication in telecommunications networks and potentially revolutionizing computing architectures with their speed and efficiency. Chemical computing explores the use of chemical reactions and molecules to perform computations. It leverages the inherent parallelism and complexity of chemical reactions for information processing. An example is molecular computing, where molecules act as computational elements to solve problems. For instance, DNA computing utilizes DNA strands to store and process information, offering massive parallelism and potential applications in cryptography, optimization, and molecular simulation. Spatial computing merges physical and digital worlds by overlaying digital information onto the physical environment, typically using augmented reality, AR, or virtual reality, VR, technologies. It enables immersive experiences where users interact with digital content in real-world contexts. An example is Microsoft HoloLens, which overlays holographic images onto the user's field of view, allowing for applications like remote assistance, training simulations, and interactive gaming experiences. Human-computer interface, HCI, focuses on the interaction between humans and computers, emphasizing usability, accessibility, and user experience. It encompasses various technologies and methodologies to facilitate effective communication between users and computers. An example is touch screens, which enable intuitive interaction with smartphones and tablets by allowing users to directly manipulate digital content through gestures like tapping, swiping, and pinching, enhancing the accessibility and usability of these devices. Adding AI to computing involves integrating artificial intelligence algorithms and techniques into traditional computing systems to enhance their capabilities. This can include machine learning, natural language processing, computer vision, and other AI methods. An example is incorporating AI into customer relationship management, CRM, software to analyze customer data, predict preferences, and automate personalized marketing strategies, improving efficiency and enhancing the overall customer experience.